Welcome back, everyone. In the last video I promised that we are going to see some applications of the light-matter interaction that we have derived in the quantum model, in particular the James-Cummins Hamiltonian and the James-Cummins light-matter interaction. And this is what we are going to do in this video. We are going to see how to create some states that are entangled states of light and matter, and sometimes states just of matter or states of light, that are non-classical, that they don't have a classical counterpart, and that they are very interesting from the physical point of view, but at the same time they are also famous in physics, and they are also very useful, and you need them if you want to develop what is called the quantum technologies. So with all this quantum computer type of bubble and technologies that are deriving out of it, you need to know these states. These are the basis of them, and we're going to derive how to, well, get them just using the light-matter interaction that we saw. So the two states that are going to see are going to be the Bell states and the Schrodinger cat state. The Bell state is a state in which you have two systems, A and B, and they are maximally entangled between these two systems that are now, it's an abstract concept, between A and B. So I wrote here the two, this is called the Bell state basis, this phi and psi plus minus, and as you can see, for example, the phi plus minus is an equal superposition between this 0, 0, so this means that the state A is in 0 and state B is in 0, where 0 and 1s are just, they are two states, 0 and 1. In our case, it will be ground and excited state of an atom, because we are gonna physically see what they are. And this state is 1, 1. And similarly to the state C, that are actually the states that we are going to generate. And these states are very important in quantum information processing and in quantum information protocols. They are used every time. And then we will also derive the Schrodinger cat state. Now, the Schrodinger cat, as you might know, is from the Gedanken experiment of Schrodinger, that if you have a macroscopic object that you can put in a quantum superposition, you would have kind of a paradox. For example, if you put a cat that is a macroscopic object and you are able to put it in a box with a certain quantum process that then can be in a superposition of states, and this process is related to the process of the cat being alive or dead, then, well, the cat can be in a quantum superposition of being dead or alive, so you could have a cat that is dead and alive at the same time, quote unquote, which is absurd, but this is the way it is. And so in general, when you have a quantum superposition of a macroscopic state, this is a Schrodinger cat state, because it's a generalization, if you want, to the Gedanken experiment of Schrodinger. And in particular, in quantum optics, the cat state is defined in this way, that I write here, that is a quantum superposition, as you can see, of two states with opposite phase, and these two states are alpha and minus alpha, but this state alpha is a coherent state of light. Why? Because the coherent state of light is the most classical object that you could have in quantum optics. In particular, if the number of photons, which is alpha square, this is the mean number of photons in the state, if this is very large, then the state behaves as a single mode monochromatic classical plane wave, and so it's a macroscopic object. It's something that you can measure in nature, in classical physics. So a quantum superposition of these two states is a Schrodinger cat state. So let's jump into it. In order to create these two states, we will need to make a protocol in time, and for that it will be very useful to compute the evolution operator. So I will do a little detour at the beginning so that we know what we have to do in order to create the states, but just bear with me. So the evolution operator. So the evolution operator is an operator that does what you would think it does. It evolves the wave function. So if you are in the Schrodinger picture, the wave function at time t is going to be defined as some unitary evolution operator u of t applied on the wave function at time 0. Right? So this operator, u, is the evolution operator, that's the definition, and is the one that is creating the evolution of the system. Now, since we know the Schrodinger equation tells us that IH bar derivative with respect to time of phi of t is equal to h phi of t. We know the evolution of the wave function because the evolution in time of the wave function is exactly what the Schrodinger equation tells you. So from here we can say that the derivative with respect to time of the wave function is equal to minus I over h bar, the Hamiltonian applied on the wave function. So as you can see, the object that is producing the evolution of the wave function is the Hamiltonian. So the evolution operator is going to depend on the Hamiltonian of the system, which is an important feature. Now, in our case, the Hamiltonian is not time dependent, so the Hamiltonian is explicitly time independent. In that case, we can integrate this equation here pretty easily. You have a function that is equal to something times the function itself, so the solution is an exponential, and in particular, the solution of this equation, if the Hamiltonian is time independent, is just e to the minus I over h bar Hamiltonian operator time t. Okay, and this is the evolution operator. This is general quantum mechanics, a specific case of a Hamiltonian that is independent of time, and we are in the Schrodinger picture. By the way, just as a comment, if you want to change between the Schrodinger picture, the Heisenberg picture, or the interaction picture, what you would need is the evolution operator. It's this operator exactly. So for example, the wave function in the Heisenberg picture is going to be it's going to depend on this evolution operator and on the wave function in the Schrodinger picture. So that the evolution in the Heisenberg picture of the wave function, it doesn't evolve in time, it's a constant. But you can compute operators in the Heisenberg and the interaction picture from operators in the Schrodinger picture and vice versa via this evolution operator. But this is just a comment. We can see it, we will probably see it in some other video, but it's basic quantum mechanics. It's not rocket science. So, okay, but now what I want is, let's calculate this evolution operator, but let's calculate it in the basis of eigenstates of the Hamiltonian, which is a thing that that has a simple form, but it allows us, since in the last video we calculated already the eigenstates of the James-Cummings Hamiltonian, we can then compute the evolution operator that the James-Cummings Hamiltonian will produce using these eigenstates that are called the dressed states that we saw in the last video. But in general, in the basis of the eigenstates of H, so we know that H applied to whatever these eigenstates are is equal to some number that is the energy applied to these eigenstates. Then this means that E to the something Hamiltonian applied to these eigenstates, because these are the eigenstates, this is to show that this is just like applying like E alpha En, so the exponential behaves in a nice way. It's an analytical function on the eigenstates. Okay, so this is true. Now, given that, well, one can say, okay, the evolution operator is, I'm gonna repeat it, e to the I h, the Hamiltonian time divided by h bar. But I can just write the same thing. Well, actually I'm not gonna rewrite it. This is the definition that we just saw. It's not the definition, but it's what it is, the evolution operator if the Hamiltonian is time independent. And now here we insert the identity, and the identity we inserted in this way. So here, this operator here is projecting onto all the possible eigenstates, but the eigenstates of the system is, if it is a complete and orthonormal set, then defines a base. So all of this is just the identity operator. This is an identity expression that is well used in all quantum mechanics in order to make some calculations. Alright, but now what we can do is we can apply the Hamiltonian using this. We can apply the Hamiltonian in this expression from the right, and then one gets that this is just the sum over n, where n is labeling the eigenstates of the system, of e to the minus I En now, because I applied the Hamiltonian on the state, so I get just the number En over h bar t, and now just the projections onto the eigenstate. So this is a very simple way of finding the evolution operator of the system in the basis of the eigenstates of a system. So this is general, and now what we are gonna do is we are gonna compute the evolution operator in the case of the James-Cummings Hamiltonian. So, because what you need to know in order to compute the evolution operator in this way is the eigenstates of the system, but the eigenstates of the system, if you remember from the last video, are plus minus n and the ground state, which was trivial, which was the ground state, and 0 G0 basically. For this to understand, you have to see the last video in which we compute these eigenstates for the light-matter interaction in the James-Cummings model. So go check that video if you don't know. And the energies of the system, the eigenenergies of the light-matter coupled system, is E plus minus m. So then we can literally substitute into this formula and find the evolution operator on the in this case. So I'm gonna be clear here. The James-Cummings Hamiltonian, I'm gonna rewrite it, is the Hamiltonian of the atom plus the Hamiltonian of the cavity plus the Hamiltonian of the interaction that we derived in the last videos that had this form, and we found out that the Hamiltonian of James-Cummings applied on the state plus minus n is equal to the energy plus minus n applied on plus minus n. In other words, these are the eigenstates of the Hamiltonian, the dressed states, and these are the energies associated with these dressed states. Alright, so in this case we are gonna write this in the I'm gonna change notation just 1 second because it's gonna be good. I'm gonna write this plus minus n, I'm gonna write it at s n, and it's just a matter of notation. So I'm gonna write this as e s n s n, and s is just a label that can be just plus or minus, so it's not a number or anything, it's just a label. And then we also have that the Hamiltonian of the James-Cummings, we know that the ground state is a bit special because there is no energy, so nothing happens with the ground state when you turn on the interaction. And we know that if you just apply the Hamiltonian of the James-Cummings to the state G0, then what you get is the energy of the ground state is 0, and the energy of 0 photons in the cavity is 0, so you just get 0. But this is the same as 0 times the vector G0. This I put it because then the energy associated with the ground state 0 is 0, so we need that. Alright, then we just use this to write the evolution operator in this case. So the evolution operator u of t is gonna be equal to, well, the first term is G0 G0. Why? Because we are using basically this equation here, and so E0 we just saw that is 0, and then we project onto the state 0. Because if it is 0, okay, if E0 is 0, then E to the I0 whatever is 1, so we just have 1. Okay. Sorry. This is getting crazy. Okay, so it's G0, G0, this projector, and then now is the sum over S, where S can only be plus or minus, and now the sum over this natural number n from 0 to infinity of E to the minus I, the energy Sn times time divided by h bar, and then the projector Sn of the dress state. This is the evolution operator of this system. And now, well, let's write it down more explicitly. So these energies E plus minus n, I recall you that they were h bar omega n plus 1/2 plus h bar omega 0 divided by 2 plus and minus, that's the E plus minus, h bar divided by 2 square root of delta square plus this capital omega n square. This we found as well, and we are gonna call this, just for the matter of simplification of the notation, h bar omega prime plus minus h bar this quantized generalized frequency, which is called capital omega n tilde divided by 2. Okay, and this is gonna be so that when we substitute all of these energies into this exponential, it's not gonna create an exponential that is very long to basically to write. But clearly this omega prime is just this, is a number, and this omega n is this square root. Alright, then we also know the expressions of the, for example, plus minus n, the projectors. So plus n, for example, we can literally write this in terms of the eigenbases that of the Hamiltonian that is unperturbed. So what I mean is the following: this plus n, we found out as well that is the cosine of this angle theta n of this minus the sine, so it's a quantum superposition of these two states with one excitation that is swapping between the two. And now if we do the bra of this operation, well, we have the bra, right? It's exactly the same thing, but I'm gonna write it for in this case, cosine theta n, and now g n plus 1 minus sine theta n, because these are real numbers, e n. So we can do the computation of this, so calculate all of that, and one just simply gets the cosine square of theta m, and then you project the first gn plus 1 gn plus 1, then plus the sine square of theta n, and then project en, and now we have the cross terms, and the cross terms can be simply written as cosine theta n sine theta n, and now we are gonna have this cross projector, if you want, gn plus 1 en plus the opposite, the complex conjugate en gn plus 1. Okay, and now it's very easy to see that if one calculates the minus here, the minus n. The only difference is that this is a plus in that case, and the cosine and the sine, well, they swap. The cosine and sine swaps, so maybe we should write it down. But I think you understand, right? So this cosine would be a sine, this sine would be a cosine, and this would be a plus. And this is the case of, I'm just saying the result of this calculation. So it's clear what we are gonna have. Okay. So let's put what we know into the unitary operator. So now the unitary operator, this evolution operator, u, is gonna be equal to g0. This is not gonna change, and then plus. And now I'm gonna perform the sum over s explicitly. So I'm gonna just write the sum over the natural number n, and now we will have e to the minus I omega prime t, where this omega prime is this. So I'm just writing this exponential, so the first term, this omega prime is t. This is gonna be common, and this omega prime, by the way, depends on n, just to be very explicit, right? Because it depends here on n. It doesn't matter, because it's a question of notation, but just to be clear. And now we will have the two possibilities. We would have e to the minus I, and now omega n divided by 2, which is this term here, t, and now plus minus, plus n plus the complex conjugate of that, e to the I omega n divided by 2t, and now minus n and minus n. So I just wrote down this expression, performing literally the sum over the two possible e plus or e minus, and using the notation that you saw for the energies, which is just simpler, and we just arrived to this equation. Okay. Okay, so now we could write literally all these terms. So we can write the unitary operator, the evolution operator for the James Cummins. If we substitute this plus n or this minus n with this expression, you get a very big expression in terms of the old unperturbed eigenstates, which is useful because typically one starts with these eigenstates, as we will see. But we don't need it, right? We know the expressions, it's implicitly written. But now we are gonna simplify a little bit what we are doing, and in particular we will consider interactions, so light matter interactions at resonance. And at resonance means that the atom or the qubit and the light that we're gonna use, they will have the same frequency. So the detuning is gonna be 0. If the detuning is 0, then this angle theta n tends to pi over 4. This we saw it as well in the last video. And so the light and the atoms are maximally entangled, if you want. Mathematically, what you see is that the sine and the cosine in this case gives the same thing, which is the sine and the cosine of pi over 4 is 1 over square root 2. Yeah. So in this case, what we have is that plus n, this projector that in general has the form that I wrote here, now is just 1/2 common factor of everything, and then we have the ground state n plus 1 ground state n plus 1 plus excited state n excited state n minus the ground state n plus 1 excited state n minus the opposite, right? En g n plus 1. This is just for the particular case in which the interaction is resonant. And for the minus n is gonna be 1/2, exactly the same things, but these are plus in both cases, but in that case everything is plus. So the terms are exactly the same, and it's just the sign that changes. Okay. And with these ingredients, we are gonna be able to calculate the Bell states. So let's enter there. I just needed some ingredients in order for you right now to understand it very easily what we are gonna do. So the Bell state generation is the following. Imagine that now we have 2 atoms and 1 cavity. So we have 1 atom here, a 2-level system that I label with 1, another atom here, another 2-level system that I label with 2, and then we have a cavity. And what we need, and a cavity. And what we need is to be able to make the cavity interact in resonance with each atom independently. So we are not going to have the situation in which both atoms are interacting with the cavity. That could be, that's a different problem. But we are going to be able to make atom 1 to interact with the cavity, atom 2 interacting with the cavity. Let's assume that the starting point of this total wave function of the 3 things, so at time 0 we start with the first atom in the excited state. So let's label it like this. So the first atom is in the excited state, then we will have the second atom in the ground state, and the third atom, and the cavity in the ground state, so with 0 photons. So there is nothing in the cavity, and the first atom is the one having an excitation. Okay, and now what we do is let's make atom 1 interact with the cavity for a certain time, and the time is gonna be pi divided by 2 omega 0. So omega 0 is just the capital omega we are seeing evaluated at n equals 0, so it's equal to 2g. This is omega 0, it's the 1 photon gravity frequency. And if you recall what we saw of the dynamics of this system, if you have the atom in the excited state or in the ground state for this purpose, and then we applied some electric field, some light for this time, this is what we called, it's very similar to what we call a pi/2 pulse. And in the pi/2 pulse, the result of that was that the atom was in a quantum superposition between 0 and 1, between excited and ground state. And this is what we are gonna get. But let's see it specifically. So what is the wave function after this interaction? And this is the reason why we calculated all these things about the evolution operator, because we are gonna use it now, no? So the wave function at time t1, which is pi/2 omega 0, is just the evolution operator at t1 applied to the 2 states that were interacting, which is this applied to the state E1 and 0 photons in the cavity, because it's the cavity and the atom 1 that are interacting. But this we can write it as E0, right? Because it's literally the state E0, and then this is tensor product with the other atom that we are not doing anything to the other atom. It's just there in the ground state, it's not doing anything. Alright, so this is the wave function at type D1. So let's calculate it explicitly using our expressions of the of this U, because we know U, we know the unitary operator U. In other words, U at T1 applied on the state E0, if you see, we are going to project. So what is doing the unitary operator is projecting, right? The evolution operator, sorry. Here, we are going to use, well, this one. So for example, this operator applied on the state E0, the first term is clearly 0, and then the other terms, this plus minus and minus, this plus minus n, they are going to have some kind of coefficients that are not going to be 0. For example, the first one, when we apply to E0, then all these coefficients, for example, that are inside here, they're going to give 0, right? Because they are in the ground state and we are bracketing with something in the excited state, is also going to give 0. So only these coefficients won't be 0. So when you do all the calculation, it's very easy to see that what you get is the following. You get e to the minus I omega 0 prime, which is the omega 0 prime, also to be clear, omega 0 prime is omega, and it was times n plus 1/2, but n is 0, so it's omega over 2 plus omega 0 over 2. This is omega 0 prime, as we define this. But as we will see, this is going to be a global phase factor, so it's not going to have any physical relevance. But okay, we have this, and then we multiply it by, and here we have e to the minus I pi over 4. This pi over 4 comes from the fact that inside this exponential we had omega n, that now is going to be omega 0 divided by 2t, but this t is t1, which is pi over 2 omega 0, so you get pi over 4. That's why we get this pi over 4 here, and now we have 1/2, and the only terms that survives, which is the E0 and the minus G1. Why there is this G1? This maybe you will, it would be nice to see it. Wow. Ahora. Sorry for that. So the E0 comes from this term, so this gives the 1/2, and the other with the minus sign comes from this term, that is the cross term. So this cross term is the one that is going to mix states. That's why we have this G1. It's easy to see if you follow the math. And then we will have, well, something very similar, e to the plus I pi over 4, 1/2, and now the state that survives here, that very easily is E0 plus G1. So this is the state. We applied the evolution operator at T1 to the state, and we see what is the state that resulted. And now what we see, we can, well, e to the I pi over 4 is 1 over square root 2 plus I 1 over square root 2. This is just, that's the number. So if you look at the terms that goes with E0, so one has E0 is going to multiply e to the I pi over 4, so it's going to multiply this. So let's say we are going to have 1 over square root 2 minus I 1 over square root 2. This is this term times E0, and now in the other side, because I'm factoring out the 1/2 to everything, you have the opposite, right? You are summing 1 over square root 2 plus I 1 over square root 2. So very clearly you get 1 over square root 2. That is going to multiply at this is 0. And if you do the same with this G1 state, then what you have is, well, it's the opposite, right? Because now the G1 here has a negative sign, so it's minus 1 over the square root 2 plus I 1 over the square root 2, and here you have the same, actually, 1 over the square root 2 plus I 1 over the square root 2, and now is the real part that goes away, and you get I 1 over the square root 2. Actually, this is times 2, and this is times 2, clearly, because you're saying 1 over the square root 2 plus 1 over the square root 2 is 2 over the square root 2, but these 2's are gonna go out with these 1/2. Okay, and so in the end, what we get is that the wave function at time t1 is equal to e to the minus I omega plus omega 0 divided by 2, which is this omega prime 0 times t1, but t1 was p over 2 omega 0, so it's this phase factor, it's a big one, and then one has 1 over the square root 2 of the state E0 plus I G1, and then, because this is the state that we just calculated right now, but then we times our product with the other atom, G atom 2, that we didn't do anything. So as you can see, basically what we did, as we were expecting, is making a kind of like a pi over 2 pulse on the first atom. So we make the cavity and the atom to interact for a time in which in the cavity there could be 0 or 1 excitation, and the atom can be in the ground or in the excited state with a 50% probability in a quantum superposition. And this is the first step, okay. But now let's do a second step, and the second step is now we make the atom 2 to interact with the cavity for a time that is called T2, that is pi over omega 0. So this is kind of like a pi pulse, right? So the atom 2 is in the ground state, so the atom 2 is gonna, if it is a pi pulse, is gonna want to go to the excited state. But the cavity, the starting point of the cavity, is a quantum superposition between 0 and 1. So let's see what happens. If we do that, then what we have is that what happens after the interaction? Well, the wave function at the time t2 plus t1 is equal to the wave function of t1 that we can write explicitly. That is gonna be e to the minus I omega plus omega 0 divided by 2t. Sorry, but this is not t, this is pi over 2 omega 0. This comes from, I'm just rewriting, then 1 over square root 2, and now what happens? Well, what happens is that now atom 1, we are not doing anything to atom 1, we are making atom 2 to interact with the cavity now. So atom 1, if everything is nice and isolated, is still, could be 50% probability in the excited or in the ground state. So let's write the excited state. Now we have to apply the unitary operator for a time t2, that is pi over omega 0, on the state of the ground state of the atom 2 and 0 photons. This was one of the possibilities, that the atom 1 was excited and then 0 photons in the cavity, so nothing had actually happened after the interaction. And the other possibility, with a X factor of I, is that you have atom 1 in the ground state, and now we apply the unitary operator u t2 on the, well, on the other possibility that I write down here, which was that the atom 2 is in the ground state, because we start with the atom 2 in the ground state, but we have 1 photon in the cavity. So the only thing we need to do now is to calculate these 2 states But again, we can just do the math because we know. For example, we know the unitary operator u at the time t2, which is pi over omega 0, applied on the state g0, which is this state, and just removing the label of atom 2. But this is not going to change the state, this is going to be g0. And if you want to refresh your mind, maybe I have written somewhere here, or probably not. Let me see if I can go back. Yeah, g0, just don't do anything. If you're in g0, the James Cummings Hamiltonian tells you you are gonna be in g0 forever. That's why the unitary operator just that's independent time. Okay, so this is trivial, and then we need to calculate just the other u t2 equals pi over omega 0 applied on the state g1. What is this? Well, let's just do the math. But now here clearly, when we applied our formula for the evolution operator, we see that t2 times omega 0 divided by 2, which is what we have in this imaginary exponential, this now is just pi divided by 2. So what we have is this e to the minus I omega plus omega 0 divided by 2, and then pi over omega 0. And then we have the two possibilities as before. This is the same calculation we did before, but now the time is different, so this phase factor is different, which makes all the difference. Minus I pi over 2, 1/2, and now the two states that survive after all the projections is G1 minus E0, and then plus something very similar, right? E to the I pi over 2 1/2, and now it's gonna be G1 plus E0. And now what happens is the following: e to the I pi over 2 is I, actually. So if you see what we are getting for G1, for example, so the coefficients here, this G1 is going to be minus I, it's going to get a minus I, and then you're going to sum a plus I. So it's actually 0. This is a quantum interference effect, in essence, deep down. So what is happening is that now there is a 0 probability that this state is possible. But what happens with the other? What happens with the E0? Now they constructively interfere, right? So you have the first one is minus I, but this has a negative sign, so it's plus I, which is 2I, and this 2 is gonna cancel with the 1/2, so it's just I times E0. In other words, the wave function of time t1 plus t2 is equal to e to the minus I omega plus omega 0 divided by 4 pi over omega 0. This came from before, from the first interaction, over square root 2, and now we have E1. Remember, I'm writing this term, so the first atom in the excited state, and then this operator gave me this. So this means that this is E1 G2 and 0 photons in the cavity, which by the way is the initial state, so there is a possibility that after all of this nothing happened. But then we also have the other probability, and the other possibility is that one have minus, this minus comes from this I times this I. You can just do the math and convince yourself. And one has e to the minus I omega plus omega 0 divided by 2 pi over omega 0, which is a phase factor. And then we have the other possibility. But the other possibility is the atom 1 in the ground state, and now the operator that we just saw that the result of all this operator, apart from this phase factor, is the atom in the excited state, atom 2 in the excited state, and 0 photons in the cavity. And now it doesn't seem like it, but we are basically done, because we can define all of these. Let's define this as a certain phase phi. So what happens is that we have that the state after the interaction, let's note as well, first of all, this is a global phase factor, right? Because this is multiplied everything, so it doesn't have any physical importance, and we can just replace it by just 1 for simplicity. And let's also recall that in the first state and in the second state, the cavity is anyway in 0, with 0 atoms. So the probability of the cavity to have 0 photons, sorry, not atoms, after these both interactions is actually 1. So the cavity is empty for sure. In other terms, we can write this as 1 over square root 2 from here, and now we have the state, excited state of atom 1, ground state of atom 2, minus e to the I phi that I just defined. This phase is just a number that depends on the frequencies of the system and the interaction between light and matter, and then the ground state of atom 1 and the excited state of atom 2, which is this state, and all of these tensor product with the cavity being empty, which is common to any case. And if you recall, if I called the ground state, I call it 0, and the excited state, I call it 1, and I forget about the cavity after the rest, because the cavity is just empty and is a separable state, is not doing anything, then what I just got is, if you want to write it like this, phi in T1 plus T2 is equal to some kind of Bell state exactly, because the definition of the Bell state, if you remember, this would be 0, let's say that the excited state is 1, then this is 1 0, and this is 0 1, and this phase factor is the one that tells me what Bell state I am in. So for example, just for simplicity, imagine that the setup, so the interaction between light and matter, is made experimentally such that this phi is equal to pi. In this case, e to the I phi is equal to minus 1, which is this minus is plus, and then what we get is exactly the state 1 0 plus 0 1, but 1 0 plus 0 1 is what we defined as psi plus, and then okay, we have the cavity that is empty, that we don't care anymore. So we created a Bell state, and this Bell state is a matter Bell state, in the sense it's 2 qubits that are entangled, but the mediator of this entanglement was the cavity. The qubits were actually interacting with light, but through the mediation of this light, the atoms got entangled between them. So just to finish the Bell state generation, let's just make it more visual. So what have we done? So let's say that we can write this as a Bell state protocol, quote unquote. There is, of course, not a single unique Bell state protocol. This is not the only way to create Bell states. It's a way of creating Bell states that has been done experimentally. Of course, experimentally you have some other problems. I'm assuming here that everything is coherent. I'm just using the knowledge we have from the James-Cummins interaction, but I'm not considering losses, that you can lose photons, that the atoms are not perfect, that line widths, etc. But we will see about it, some of these aspects in the future. But okay, how was this Bell state? Well, we started with a qubit, another qubit, and the cavity, and the first qubit was in the ground state, the second was in the excited state, the second or the first, it doesn't matter, one of them was in the excited state and the other was in the ground state, and the cavity was empty. And what we did is, this qubit here the second one, we make it interact with the cavity. Let's define it, or let's visually write it in this way. So here time is going in this direction, and this time was t1, that was pi over 2 omega 0. Okay, now after this interaction, what happened was that the cavity was in a superposition. Let's write this explicitly. After this interaction, what we made is the cavity is in a superposition of 0 plus 1, and the qubit is in a superposition of ground state and excited state. This is the states if you only look at the cavity or only look at the qubit, because they are entangled as well. In other words, if the cavity is in 0, we do know that the qubit then is in the excited state, and if the cavity is in 1, we do know that the qubit is in the ground state. So be careful. It's a nuance, but it's important. And then after this interaction, the first qubit, we make the first qubit interact with the cavity, so light matter interaction, for another time, and this time is t2, which is pi over omega 0, so it's double the time of the first interaction. Here, of course, all the qubits and the cavity have all the same frequency, everything is tuned in resonance. Here these lines, I made them with the dash lines. And then what we saw is that the final state is that the cavity is exactly with 0 photons, so the cavity is as it started, but these two states form a bell pair. In particular, well, it could be phi plus or minus. It could be even a generalized bell state, but this is a bell state. Alright, and this was our protocol to create bell states, which I think is pretty cool. And I hope you are with me. It's pretty cool. Anyway, now let's see if we can create, to finish this video, the Schrodinger cat states. Schrodinger cat state. Okay. And for this, I need the evolution operator, but it's gonna have a simpler form, because here, let's see what happens to this evolution operator that we just calculated if the detuning is much bigger than the interaction n for all the Fock states n that are gonna be relevant. So for example, if we have a coherent state alpha, that is the case that we will have, then the mean value of n is equal to alpha squared. And what we are saying more or less is that the detuning should be much higher than omega of alpha squared. That's all the possibilities. Okay, it's an approximation. So if this happens, then if you remember that we have this delta squared plus omega n squared, this can obviously be rewritten as delta square root 1 plus omega n squared over delta squared. And now we can, since this quantity is very small, if this condition is fulfilled, then this is almost equal to delta that multiplies, and now we replace by the, well, we do a Taylor series expansion and take the first term, which is 1 plus 1/2 of this, so one gets 1 plus omega n squared over twice delta squared. But now we can redistribute the delta inside, so this is delta plus omega n squared over 2 delta. Okay, this is just some math. And what we also know is that if delta is much bigger than omega n, then this angle that I defined theta n, that was telling me how mixed light and matter in eigenstates were, tends to 0, and we recover the eigenstates of the unperturbed Hamiltonian. In other words, in physical terms, means that if the detuning is very large, then the atom, the qubit, and the light cannot talk to each other, and so there is no interaction. So the eigenstates of the Hamiltonian are the eigenstates of the atom is there and the cavity is doing its thing. So this angle goes to 0, means that this plus n state is going to be basically the excited 0, not 0, sorry, the excited n, and the minus n state is going to be basically the ground state n plus 1. Well, if I write it like this, yes, it's exactly like this. Okay. So, the evolution operator, we can write it using these two things that we found. So it's the evolution operator when this delta is much bigger than omega n. This is typically called the dispersive regime. So it's when you have the two systems, atom and light, that they are far detuned, so they don't talk to each other, but actually there is some kind of interaction between them. This is very subtle and it's a little bit more complicated than what we are doing here. What we are doing here is a crude estimation, but it just helps to understand why the Schrodinger cat state will arrive. But in the following video, very soon, we will see, we will dedicate a video to the dispersive regime, in which case, because we have to break some of the approximations we made to arrive to the James Cummins Hamiltonian. It's actually not the James, it doesn't come from the James Cummins interaction, but if you do this type of operations, of approximations to the unitary evolution operator, you get actually to a result that is correct. But we will get explicitly to this result that is correct doing some other physics in the dispersive regime. And in particular, we will do what is called a Schrieffer-Wolff transformation, and we will explain what it is, and it will be interesting. But for the purposes of this video, this is perfectly correct, that the evolution operator now, if we just apply what we know, is G0, G0. This is the case all the time, because this state doesn't change, even if the interaction is on or off. And then plus, now we would have the sum over the natural numbers n e to the minus I omega plus omega 0 divided by 2t. This is the same as before, nothing happened. And now what happens is that now this simplifies, the part that is inside simplifies quite a bit. We just have e to the minus I delta divided by 2 plus omega n squared divided by 2 delta, well, 4 delta actually. This is from this term, that is 1/2 this term, which is exactly what I wrote here. T, and then one has en, and then plus something very similar, e to the plus I, and then all of that, right? All of this, and then g n plus 1, g n plus 1. So as you can see now, the projectors, there is no cross term. There is no term en, g n plus 1 or vice versa. This is because since they are very far detuned, they are not interacting. So the two systems, they are not producing transitions. So if I have the cavity at 0, then the cavity will continue at 0. And if I have the ground state of the qubit, then the qubit will be always in the ground state. And if I have the excited state of the qubit will always be in the excited state. So they are not going to change. But as you can see, there is a phase factor. So there is some kind of reminiscent of the interaction. There is some interaction between the system, because this phase factor could be important. It's going to be important. And this phase factor, recall that depends on n. Depends on the number of photons. And depends on the state of the atom. So the cavity will get a phase factor that is different depending on the atomic state. In particular, is e to the minus I something or e to the plus I something. so there is some angle there. Let's see what happens explicitly. There is a phase shift to the eigenstates that depends on the atomic state and also depends on the Fock state in particular we are looking at. And now what we are going to do is we are going to create a Schrodinger cut state with this. And for this we need a qubit and we need a cavity. And we need the qubit to be in a quantum superposition between ground state and excited state. But we know how to do that. We just did it before. So okay, we can say that there is an external cavity, like another cavity, that we make this other cavity in resonance. So with delta equals 0, the tuning 0, we make this cavity to interact with this atom. And now this cavity, we completely forget about it. We don't want it anymore. If we look at it, it would be in 1 over square root 2, 0 plus 1, but we just don't care. Like, we literally don't care. And we use this state here, but the state of the qubit here is clearly 1 over square root 2 ground state plus excited state up to a phase factor that depends on the time of the interaction. So I'm gonna, the time that you wait, so I'm gonna just assume this is the state, which is true, and then the cavity, importantly, is gonna be in a coherent state, which we need. Alright, and now what we are gonna do is we are gonna make this cavity, let's put this interaction, let's visually write it like this. So why I write the interaction different? Because this interaction is in resonance, so they are swapping energy between the two. And in this interaction, I'm assuming that this state, this cavity, has a frequency such that this is true. Let me write it better, because maybe you don't see. So I'm assuming that here the detuning is much bigger than this omega alpha square, where alpha is the coherent state, the mean number of photons in the coherent state. So I'm assuming basically that the detuning is very big. And then, well, let's see what happens to the cavity and to the atom. Now, to the atom in particular, not much is going to happen to the atom, because when we apply the unitary operator, is what we are going to do, well, the atomic state is not going to change, and you will have maybe a phase shift between the ground state and the excited state, depending on the number of photons. Which, by the way, I'm saying that nothing happened, but actually this is very important that happens, because this is what allows to resolve Fock states in some experiments, and these are very cool experiments. But we are not going to be interested in that. What we are going to be interested right now is what happens to the cavity. What is the state of the cavity after this interaction? And let's see explicitly what it is. So we can see explicitly what it is by assuming that then what I just wrote is that the quantum state of the qubit and the cavity at time equals 0, so the beginning, the state of the system is just 1 over square root 2, and now one has the qubit in the quantum superposition between ground and excited states, and then we have separately a phase, a coherent state. So recall, because this is going to be very important, the coherent state, this comes from quantum optics, but we wrote it already, we used already this. The coherent state is just defined as this state, e to the minus alpha squared divided by 2, this is just a normalization factor, and then we sum n from 1 to infinity of alpha to the n divided by square root n factorial, and then n. These n are the Fock states, because we know how the evolution operator affects the Fock states, but so we can write any state in quantum optics as a superposition of the Fock states, because the Fock states are a complete basis. So this particular one is the coherent state, which is the state we are interested in. Of course, we can say that this is, we are writing this, right? We are just writing a superposition of Fock states that gives you the coherent state, and these Cn are exactly these coefficients that you can see what they are. This means that if I have a Fock states m and I make the overlap with the coherent state, I just get Cm. This is remember that. Alright? Because now what we do is we apply the dispersive unitary evolution. With dispersive, what I mean is that we are applying this one. So this I called it ud. D is from dispersive, but just forget about it. It's just this operator that we derived before. And so we apply the operator to the state at 0 to get the state at t. And well, this is just 1 over square root 2. And now we apply the operator u d of t to the state g alpha plus the same thing u d of t applied to the state excited state alpha. Okay, so what is the state at the end? Well, let's see. Well, this of course is psi of t, right? Just by definition of the evolution operator. And now what we get is the following. So ud of t applied to the state g alpha, this gives the coefficients that I just wrote, but because it's gonna be easier, so let me tell you how this is done. This is perfect. Okay, so when we applied u to the state alpha, alpha is a superposition of all these states, right? But this means that when we apply, for example, I don't know, some kind of a state of the atom, G or excited state, and then M, and we apply it to this state alpha, then we are gonna get C, well, whatever, G or E, we are gonna get exactly Cm. So the coefficient associated with this Fock state. So when we apply this alpha, the only thing we get, for example, the first term is gonna be clearly C0 and then G0. Why? Because this is the coefficient associated to the Fock state of the cavity being empty, and of course is the u dt, the first thing that the evolution operator does is to project onto this state. You can make the math explicitly, but it would be a bit long to do it exactly. So I hope this is more or less clear. Otherwise you can convince yourself by doing it a little bit. It's not hard. Well, plus, and then we get the sum of n from 0 to infinity, and here we get what I called, and I will define it now, e phi 0 and e psi of n, and then we get Cn and then G n plus 1. Now this phi 0 is just is a definition. This phi 0 is gonna be this one, so it's omega is omega plus omega 0 divided by 2 times the time t, that is unspecified, and this phi n is gonna be delta divided by 2 plus omega n square divided by 4 delta times t. So it's the phase. So these phases depend on time. Be careful, because I'm not writing it explicitly. And the second phase in particular depends on m, but if you see, depends on n linearly, because omega n square is omega n square is 4 g square times n plus 1, just by the definition of omega n, no? Just to be mega clear, omega n is 2g square root n plus 1. So we divide by delta, well, by 4 delta actually. Here what we actually have, just to be explicit, is g squared divided by delta times n plus 1. So this is important, it's in the exponential, that is linear in the exponent. Okay, but then it's easy to see that, well, let me tell you some other things. Why we are getting this is when we apply the unitary operator, all the terms that are with the excited states are zero, because we are going to project something that is the ground state on this excited state, so all these coefficients are zero, and the ones that are not zero are they just give you the coefficient of the M Fock state that is inside this coherent state. It's easy to see. But now this is linear again. This is linear in n, so this gives you something that is e to the I some number. Let's not call it alpha because it's not a good let's call it beta, but it doesn't matter, some number times n, which you can always write. We have a coefficient that is going to have some alpha n over the square root n factorial, but this can be written as alpha e to the I beta to the n divided by a square root n factorial, blah blah blah. Here what I want to say is very hand-wavily that these coefficients Cm or Cn are these coefficients inside, and inside this sum there is an alpha to the n, but since you are multiplying by e to the I n something, you can always write it as a new alpha e to the I something else, this something in particular g squared over delta elevated to m. So this means that we can define a new coefficient that is alpha e to the I beta, and we have a new coherent state. In other words, all of this is to say that this state is easy to see, that this state G, because everything is ground state of the atom, which is understandable because now the dispersive interaction is not going to make the atom to transition, but now a new coherent state that is alpha e to the, I'm going to write it like this, I psi, right? And this doesn't depend on n because all the dependence went out because of the infinite sum, that we need the dependence on n here in order to define the new beta, just to be clear. Okay, and this c is basically g squared divided by delta. So the how much the both things are interacting divided by t, so the time. How much they are interacting divided by how much they are far away. Okay, they have to be sufficiently far away so that all these approximations we made at the beginning hold. That's also true. Anyway, this is the case. Then the dispersive interaction applied to the state E alpha is going to be something very similar. In this case it's even simpler. We will have the sum over n, we will have some global factors that we don't care, e to the minus I phi. But now importantly, the sign of this exponential is negative because this exponential was the one associated with the en. Then we will have, this is phi n, then we will have the coefficients and then en. So it's just a phase shift. But this phase shift depends on the number n, such that it's clear to see that this we can write it again as some, actually here is very easy to see, some kind of global phase factor. And now the excited state, because it's the excited state all along. And then with the Fock state we basically created a new coherent state that is just a phase. It has, this coherent state by the way has exactly the same number of photons, which is the modulus of alpha e to the I, which is the modulus of alpha squared, which is the same number of photons at the beginning at the end, which makes sense because the atom again is not talking with the light, it's just giving a phase shift. This phase shift is due to what they are called virtual processes, but we will see about them in the dispersive regime. They are interesting. It's a consequence of quantum field theory as well. It's a consequence it's a consequence of quantum mechanics, but okay, so it's gonna be the same as before, right? But with a sign, a negative sign, clearly. This phi is exactly the same. But this means that then what we found is the following. We found that the state psi at time t is equal to 1 over square root 2, and now we have the ground state alpha e to the minus I phi plus the excited state alpha e to the, sorry, here is well, it doesn't actually matter, but let's write it as we were writing it here. Here is positive and there is negative. But now if you know a little bit about coherent states, you would know that if we go to phase space and we have a state that is a coherent state in phase space, so this is x, and p is, this is the phase space of the coherent state. X is a plus a daga basically, and p is a minus a daga times I. So these are the two quadratures. I'm assuming this is known, this is basic quantum optics. This is the state alpha. Now, because of the interaction with the atom, we have these new states in a quantum superposition. So if this is an angle psi, now we have this state here. This state here is actually alpha e to the minus I psi, and exactly with the same angle psi, this state here is alpha e to the I psi, right? Okay. And now what we have is, this is the initial state if you only look at the cavity, but when you look at the cavity after the interaction at time t, what one has is this state of the cavity. It's a quantum superposition between these two states. So now let's imagine that we set up all the experiment and everything such that this angle phi, that depends on g, that depends on the tuning and so on, and depends on the time that you are interacting. Let's make this angle to be exactly pi. So in this case, e to the I psi is equal to minus 1. And e to the minus I phi is equal to 1. So this means that the state that we have is 1 over square root 2, and now we have the ground state alpha, or minus alpha actually, plus it doesn't matter, the excited state alpha. So if we forget about the cavity, about the atom, we don't care where the atom is, we just leave the atom away, then the cavity, this is technically called trace out the other system. We just look at what happens to the cavity, what is the quantum state of the cavity. Then the cavity is in a state which is 1 over square root 2, is in a quantum superposition between minus alpha and alpha. And this is exactly a cat state, right? That I am gonna write it, just, it's a cat state, okay. This is just a cat state. So we created, using the dispersive interaction between an atom that was in a quantum superposition and a cavity, we created a Schrodinger cat state inside the cavity. And I think that's pretty cool. So to recapitulate and to finish this video, to finish off this video, what we have done is, to create the cat state, is we have a cavity that is an auxiliary cavity. We make a pi over 2 kind of interaction of this cavity with an atom, or with a qubit here. So the qubit starts in the ground state, then it interacts with this cavity. After the interaction, the atom is just in G plus E over square root 2, so it's in a quantum superposition. And then if we make a cavity that is far detuned from the atom interact dispersively for a certain time t, and we select the time t appropriately, Then at the end, if you just look at the cavity, here you created a Schrodinger cat state. And with this, we finished. I think it's a good place to stop. And we finish these applications of Bell states and Schrodinger cat states. I hope you liked it. I think it's very interesting to see how these states appear. In quantum information, one can understand that using quantum circuits you can create these kind of correlations, which is interesting, it's nice in itself, but it never tells you how you do it physically. So what are the ingredients physically that you need? In this case, one way of doing it is the interaction of light with matter, which I think is pretty cool to see. And in the next videos, what we are gonna start exploring is the dispersive regime that I told you about. We will try to see what they mean. The dispersive regime is very important for a concept that is called quantum non-demolition measurements, and this will allow us to understand and to explain one experiment in particular from 2012, in which you can see the quantum fluctuations of photons at real time, and I'm gonna explain that experiment from the explanation of our dispersive regime and what we know already from the non-dispersive regime, so when the atoms can be in resonance and they can exchange energy between light and matter, and we're gonna see about it. And then in the future we will continue exploring light matter. Probably we will open the system and we will see what happens when we have losses and we have to compute master equations. And in the meantime, as well, it's probable that we will do some shorter videos on some mathematical tools that we will need from quantum mechanics. This evolution operator, for example, is a clear example. Probably we will put the different pictures, Heisenberg picture, Schrodinger picture, as a refresher for everyone. And we will build up some kind of knowledge in this sense, so everyone can be in the same page easily. So I hope you liked the video, and I'll see you in the next one. Ciao, ciao.